Let's start now on an example that looks kind of long, but hopefully you'll see is a straightforward application of the things we just discussed. So we have a circuit that has a 9-volt battery, and it's connected to a 4 microfarad capacitor and a 25 ohm resistor, and it's got a switch in it that can flip from position A to position B. It says the switch in the figure has been in position for a long time. So this is telling us that the capacitor is fully charged. The amount of charge on the capacitor is a maximum, that's the amount QO, and the potential across the capacitor initially is the full 9 volts. It changes to position B, so we flip the switch at T equals 0. And that's when the charge starts to leave the capacitor plates and current flows around the circuit for a time. So what is the charge QO on the capacitor immediately after the switch is closed? So we'll remember that capacitance is charge over potential. So our initial charge QO is the capacitance times the initial potential of the capacitor, the full 9 volts. So we've got our capacitance, which is 4 times 10 to the minus 6 farads times our initial potential of 9 volts. That gives us 36 times 10 to the minus 6 coulombs, or 36 microcoulombs. So the initial charge on the capacitor is 36 microcoulombs. What is the current I through the resistor immediately after the switch is closed? So as soon as we flip that switch, the current starts to flow around, those charges start to move, so we do get a current. So the initial current through the resistor can be found by finding the potential across the resistor. And if we've got 9 volts across the capacitor, it means we've got 9 volts across the resistor divided by the resistance. So we've got 9 volts divided by 25 ohms. So we're just using a straight up Ohm's law there, 0.360 amps. Okay, there's part B done. Part C, what is the charge Q on the capacitor at T equals 50 microseconds? So for part C, and actually part D is going to use the same method, C and D, we want to find the charge. We remember Q is equal to Q0 times e to the minus t over tau. Tau, remember, is our time constant. So in our equation here, QO is our initial charge, 36 microcoulombs. Tau is our time constant, equals R times C, 25 ohms times 4 microfarads. I'm going to work in micro units here because my time is given in microseconds. So 25 times 4 gives me 100. Ohms times microfarads gives me microseconds. If you prefer to work in seconds, then this would be 100 times 10 to the minus 6 seconds. So for C, our time equals 50 microseconds. This gives a charge, I'll do 36 microcoulombs times e to the exponent of minus 50 divided by 100. And that gives me a net charge of 21.8 microcoulombs. So it's gone down a fair amount. Part D, my time is equal to 100 microseconds. When I put this in my equation, I get my charge equals 4.87 microcoulombs. Okay, part E and F. That asks for the current at 200 microseconds. Oh, sorry, I mixed up what I answered. I labeled it C and D. Really, it was C and E asking for the charge. The next two parts are D and F, so I did them a little tiny bit out of order. Sorry about that. So C and E asked for charge. D and F asked for current. So for my current, I equals I0, e to the minus t over tau. We found that on a previous slide. So for part D, t equals 50 microseconds. We'll plug in that our initial current I is 0.360 amps. So my current I at 50 microseconds is going to be 0.218 amps. And then for part F, our time is 100 microseconds. And that gives us a current I of 0.0487 amps. Okay, this one was pretty straightforward. So let's do another problem, which is a little bit of a combo problem. The capacitors in the figure are fully charged and the switch closes at t equals 0 seconds. So let's just take stock and see what happens. We have 3 capacitors and they're all fully charged up. That means that as soon as we close the switch, as soon as we complete the circuit, current is going to flow, current I. The initial current will be I0 and it will change over time as the energy gets dissipated through the resistors and we lose charge on the capacitors. Current is going to flow through the whole circuit. So the tricky part about this is that it doesn't look like the circuits we've just had. This has combinations of capacitors and resistors. So what we have to do is solve the combination circuit first. Let's find an equivalent circuit, and then we can worry about the current through the 8 ohm resistor. Okay, so let's start with finding our equivalent circuit. So I'm just going to real quick re-sketch the circuit we have. I've got a 60 microfarad capacitor connected to a 60 microfarad capacitor, and that's in parallel to a 20 microfarad capacitor. I've got an 8 ohm resistor up top, then it comes down and it connects to a 20 and 30 ohm resistor where they're in parallel. So this is what my circuit looks like: 20 ohms, 30 ohms, 20 microfarads, and 60 microfarads each out here. This is 8 ohms. So let's think about the things we can find equivalencies for. I'm going to do resistors first. So the 20 and the 30 are in parallel because they're connected top to top, bottom to bottom. I know to find an equivalent resistance, I'll do 1 over R equivalent equals 1 over R1, that's 30 ohms, plus 1 over R2, that's 20 ohms. If you wanted to do a common denominator, 1 over 30 is the same as 2 over 60, and 1 over 20 is the same as 3 over 60. You don't have to do it like this if you don't want to. I'm kind of a fractions person, so that's more my way. If you wanted to do numbers, that's fine. So 1 over R equivalent is 5 over 60 ohms. Take the reciprocal of both sides. R equivalent is 60 ohms over 5, or 12 ohms. Okay, what other connection can we catch? Well, the two 60 microfarad capacitors, they're in series. I'm going to feed 2 birds with 1 scone here and do a couple of calculations in the one circuit, and then I'll simplify again in the next step. So when you have capacitors in series, you have to find the equivalents by adding up the reciprocals. So 1 over C equivalent is 1 over 60 microfarads plus 1 over 60 microfarads equals 2 over 60 microfarads. So to get the equivalent capacitance, take the reciprocals of both sides, 60 microfarads over 2 to give me 30 microfarads. So now I'm going to pop out those 2 resistors, put in the equivalent, pop out the 2 capacitors, put in the equivalent, and see what I can simplify from there. Let's start with the new equivalent circuit diagram. Still got my 8 ohms on top. I've taken out my 2 resistors in parallel. I've put in an equivalent resistance of 12 ohms. Then on my left-hand branch, I've popped out my 2 60 microfarads and I've replaced them with an equivalent, which is 30 microfarads. And that's in parallel with a 20 microfarad capacitor. Then they're connected along the bottom. If I look at my connections now, my 2 resistors, the 8 and the 12, they're in series. To find the equivalent, I can just add those guys up. 8 ohms plus 12 ohms to get 20 ohms. And my 2 capacitors, they're in parallel. If you add capacitors in parallel, to get the equivalent capacitance, you just add those up. So my equivalent capacitance is 30 microfarads plus 20 microfarads equals 50 microfarads. Okay, next step, I'll draw one last equivalent diagram and then we'll apply what we know about RC circuits. So let's draw that last equivalent diagram and take stock of what we have. So in our last equivalent diagram, we've got an equivalent capacitance of 50 microfarads. That's connected by a closed switch to an equivalent resistance of 20 ohms. So here's our RC circuit. We've got a fully charged 50 microfarad capacitor connected to a 20 ohm resistor. We know that when that switch is closed, the current starts to flow. So I've got the original diagram here as well as the new reduced diagram. So both circuits, because they're equivalents, both circuits have the same current flow. If you look at the top diagram, that current I goes right through the 8 ohm resistor. If you look at the bottom diagram, that current I is the one that flows through the circuit. So we're asking about current I. Let's see what the problem is telling us, what our setup is. It says, at what time has the current in the 8 ohm resistor, so that's current I, decayed to half the value it had immediately after the switch was closed? So our setup is that our new current I is equal to 0.5 times the initial current. So there's our setup. That's the problem we have to solve. Let's remember that current I is equal to I0 times e to the minus t over tau. So our new current I is 0.5 times the original current I0 equals I0 e to the minus t over tau. I've got an I0 on both sides, so you can divide both sides by I0 and they cancel. That leaves us with 0.5 equals e to the minus t over tau. If we want to get rid of an e, we have to take the natural log of both sides. Natural log of 0.5 equals minus t over tau. We're trying to solve for t because we're asked for how long does it take. So t then is equal to minus tau times the natural log of 0.5. And at this point, we might remember that tau is equal to r times c. Minus rc times natural log of 0.5. Thought I was going to get it all in on this slide, but I'll need to spill over onto the next one. So to finish up, all we have to do now is to fill in our R, which is our 20 ohm resistor, our C, which is our 50 microfarad capacitor, multiply that by the natural log of 0.5, which you can do on your calculator. That turns out to be 0.000693 seconds. You can write it like that or in scientific notation, or I'm going to write it in milliseconds, 0.693 milliseconds. So that's how long it takes to decrease to half your original current.